Hi, everybody. We're going to give it another minute or so to see if we can get other students attending. You guys all had a good weekend? All right. So I'm going to finish up chapter 1.2 today. I'm going to finish up chapter 1.2, and we are going to, I've got some lecture examples to finish up and just a couple concepts to finish up. And then we're going to jump into chapter 1.3, which is a very exciting chapter. And then we will try some of our classwork stuff. Don't forget the classwork, we're gonna have a quiz this Thursday, and I'll collect the classwork on the quiz time. And the classwork, I'm looking for attempt. Okay, have you made a concerted effort or just tried it? You don't even have to complete the whole thing, but have you at least tried, a bunch of the problems? It's gonna really help you study for the quiz. But remember, the quiz, I think it's just chapter 1.1 and 1.2. Okay, we're gonna have a quiz on 1.3 and other stuff later. Okay. All right, so let's just remember where we were. So chapter 1.2, we were talking about how do we represent lines. We did last week, we were talking about lines using a vector equation. Okay, so when we think about lines, we think about algebra, and we think about y equals mx plus b. But we want to be able to take out of context, out of the coordinate axis, our representation of a line. So we want to be able to represent it using a vector. Now, a vector equation for a line, okay, has a point on the line, that's our x naught, and it's being added to a vector that's parallel to the line. So this is how we think about it. X naught is our point on the line, okay, and v is our vector that's parallel to that line, okay. T is a parameter that gives us that scalar multiple on our vector to help us generate points along that line. X bar is our generic representation for our line itself that represents both x and y, or x, y, and z if we're in 3 dimensions, okay. X naught, actually we put a bar over it because it has multiple components in it. It has an x component and a y component, or x, y, and z, depending on our dimensions. Okay, our vector is going to have the same dimensions as the dimension that we're in, and t is the scalar. It's an all real number, okay. I take my vector equation, I can break it down into component pieces. So x is going to be x naught plus t v1. v1 is my x component of my vector, and y naught plus t v2, same t in both of these, okay? Which means I can take this equation, solve for t on each, and then set things equal to each other and get what we call a symmetric equation. All 3 of these equations are essentially just different ways of representing our vector equation. Okay, so we'll want to be able to think about that, right? How we do that. So last week we were working through our example problems, and we looked at if we had 2 points. Okay, we can choose which one we want to be a terminal, which one we want to be an initial. We want to come up with a vector equation. The vector is going to be the displacement vector between those 2. So depending on which one I choose as the terminal or the initial, my vector will point in this direction or it will point in that direction, okay? Whichever one I choose as the initial point becomes the point inside of my equation, my vector equation, okay? So now the next question, the reason I'm reviewing that one, it says because example 4 says we want to be able to write the line from example 3 as an equation for a line segment between the 2 points. So as though I were to have a line segment. So let's remember the line itself was x bar. I'll use this one, 3, 2 plus t minus 4 minus 7. I'll just choose this one, okay? So if I wanted to be, before we had it as a line, but if I wanted to be a line segment between these 2 particular points, right? So the 2 points that we had on here, 3, 2, and then we had minus 1, minus 5. Okay, if I want that to be a line segment, right? So instead of it being an infinite line, which had arrows in both directions, to be a line segment, I have to restrict my t in order to be between 0 and 1. be between 0 and 1. So how we say that to make it a line segment, I write my vector equation plus t, same thing as I would normally. So I do, oops, 7. So I do everything the same as I would otherwise. And now, instead, at the very end, I say 0 is less than or equal to t, which is less than or equal to 1. Now, why did I restrict it between 0 and 1? And the reason is because if I choose t equals 0, choosing t equals 0 and t equals 1 will give me the endpoints. T equals 0. Let's plug that in. So if I choose t equals 0 and I plug it into here, so if I go 0 times minus 4, 7, I'm going to get a 0. So then the point that I get is just equal to 3, 2. That's this endpoint right there. If I choose t equals to 1, that's my other endpoint, right? You can imagine what's going to happen. I'm going to go, this is going to be 3, 2 plus 1 times minus 4 minus 7, which is going to be 3 minus 4, 2 minus 7, which gives me my other endpoint, okay? So these here form the endpoints of our line segment, okay? So restricting t to be between 0 and 1, I can choose any value I want between 0 and 1, and that'll fill out the line in between these two endpoints, but restricting t as the boundary points between 0 and 1 makes it a line segment instead of a line. Okay, so each one of these, okay, this is my infinite line. You can see the arrows mean it's an infinite line. I can choose any value for t that I want. I'm not restricted. It's an infinite line. If I restrict t to be between 0 and 1, I'm going to get a line segment. Okay. All right. So I guess I'll have that written down. If anybody needs more time to write that down. Okay. What I want to do is I'm going to talk about, this chapter was about lines and planes, so I'm going to jump into talking about planes, and we're going to spend a lot of time on plane representations, equations for a plane, but what we want to do today is first, right, we're going to talk about a vector equation for a plane. So just so you have it, we represent our plane using different types of equations, but I want you to make sure that you have the vector equation for it. So let's draw out our plane. Now this is an infinite plane. It's infinite in all directions, but I can't draw an infinite plane, so I just draw it like this, as though this is just a representation of our infinite plane, okay? So now you can imagine, say I've got, you know, multiple points along this line. If I've got point A, and I have a vector here, and I have another vector here. So I have V1 and V2. These are two vectors on the plane that intersect each other at point A. So two vectors on the plane that intersect each other at point A, okay? And A will represent as x naught, y naught, oops, and that should be z naught. Okay, we're in 3 dimensions, right? So I have an x, y, and a z component. V1 and V2 are 3-dimensional vectors as well, okay? Now, the only thing that we need to make sure that we say is, I've got these two vectors, and they are not parallel, okay? So they're not parallel. They're going to be intersecting each other at some point, okay? So I'm basically kind of zooming in my focus on that spot where those two vectors are intersecting each other, okay? So now what I can do is I can say I'm going to need 2 parameters, right? I'm going to need T1 and T2 to help me represent the plane equation, okay? And plane that intersect each other at point A. Okay, good. All right, so now I can say my vector equation for the plane looks like this. We don't really use this representation that much, but I just want to make sure you have it. X bar, which is our generic representation, that's our x, y, and z, okay, our generic x bar equals And I can say this is plane of, and it's, my parameters are T1, T2, okay, which now I'm going to write it as x naught. This here, this was our A, I'm going to call this x naught with a bar over the top, okay? X naught is our point on the plane, okay, plus T1, V1. T1, our first parameter, is associated with our first vector, plus T2, V2. I mean, it's arbitrary. I could have put T2 in front of V1. It just makes more sense to have them have the same subscript. Okay. And again, like we did with our line, this can be broken down into different components. So x would equal my x coordinate, my y would equal all the x portions, my z would equal all the x portions. And I would have essentially, 3 equations, right, and 2 unknowns. T1 and T2 are going to be our unknowns. Okay, so we're going to do an example so that you can see how we actually, pull this together into an equation. Like I said, we don't really use this representation all that much for a vector equation for a plane, but I wanted to make sure that you have it, okay, so that you know what I'm talking about. All right, so keep that in mind. And then I pull out my lecture examples again. So this is example 5. I've got 3 points. This is an R3. Write the equation for the plane containing these 3 points. So we're going to use a vector equation. We're going to do a vector equation for these here. Okay. So what I like to do is I kind of like to visualize here. And I'm not going to worry. I could, plot these on a coordinate axis and then, come up with, like an exact, concept of where these points are located with each other. I'm not a very good artist, so that it's harder for me to plot this. So I just tend to kind of do it stylistically. So this is, I'll write this out as 2, 0, 2. I'll call this one 1, 0, 0. This point here, this point here. And that's going to make this one -1, 2, 0. Now we want all 3 of these points to be on the plane. Okay. So what I need to do is I need to choose one of these points as what we call our initial point. Because what I'm going to do is I'm going to calculate a displacement vector. I'm going to calculate V1 and V2 are going to become displacement vectors between these pairs of points here. Okay, so that's that one. And then our second step is we're going to calculate 2 displacement vectors. And this will become V1 and V2. Okay. And that's why I need to choose one of these as the initial point. It doesn't kind of matter which one you choose. I tend to choose the one that has the most zeros in it because, I have to subtract. So I think I'll choose, so let's do this. We'll calculate, I'll choose 1, 0, 0 as my initial point. Okay, if I choose that as my initial point, like I said, it's arbitrary, but I'm choosing it because it has the most zeros in it. So now when I want to calculate V1 as my first displacement vector, so I'm gonna just draw it out so I can visualize. So I'll call this V1 and that V2. Okay, so V1, remember, it's going to be terminal minus initial. So terminal, I'm going to go 2, 0, 2 minus my initial 1, 0, 0. Okay, so this is 2 minus 1, that's 1, 0 minus 0, 2 minus 0. So that's equal to V1. Okay. Now remember, I want these displacement vectors to intersect each other, so I'm going to choose the same initial point. So this is the first displacement vector, this is the second displacement vector. Okay, so terminal minus initial, so my terminal point is -1, 2, 0, right here in this spot, -1, 0, 0, the same initial point that we had on the other one. Okay, so I'm going to go -1, -1, so that's -2. 2 minus 0, 0 minus 0. Now I have V1 and V2. I have my initial point. So now my vector equation for my plane, my P, is going to equal to, remember, I'm going to write it out, x naught plus T1 V1 plus T2 V2. I'm just going to plug things in. T1 and T2 are parameters. Those are going to be values that I'm going to choose. So they stay as variables. Okay, so my vector equation for the plane becomes x bar equals my point 1, 0, 0 plus t1 times v1, 1, 0, 2 plus t2 times v2 minus 2, 2, 0. And there's the, oops, can you see that? Our vector equation for this plane, okay? We're going to talk in later chapters about other representations, other equations for representing a plane, okay? But the vector equation for the plane is the most simple. Okay? I just need two displacement vectors and two parameters and then a point, okay? Right, now I can break this down into different pieces. So if I break this, I'm just gonna, I'll do it in different colors so you can see. So this answers our question here. So if I want to get a point on the plane, generate a point on the plane, what I'm going to do is I'll break this down into different component parts. So x is equal to 1 plus t1 minus 2 t2. So all I did was take my x coordinates, okay? Y equals 0 plus 0 times t1 plus 2 times t2. Z equals 0 plus 2t1 plus 0 times t2. So these here are going to help me generate a point on that plane, okay? So I have to choose random, whatever I feel like random values for t1 and t2, right? So I can just pick and choose, you know, whatever values that I want for there. So if I choose just randomly, if I say t1 equals to 2 and t2 equals to 3, okay? So I'm trying to generate a point on this plane. So when I do that, I'm going to say x is equal to 1 plus t1 minus 2 times t2. So 1 plus 2 is 3, minus 6 is going to give me minus 3. Y is equal to 2 times t2. So that's 2 times 3. That's equal to 6. My z is equal to 2 times t1. Is equal to 4. So a point, a possible point, a potential point on the plane is minus 3, 6, 4. That's one point on the plane. Remember, this plane is infinite, so we have actually an infinite number of points. Because I have an infinite number of possibilities I can use to choose for T1 and T2. But that's how we would generate a point on this plane and thereby build it up by essentially working through. Okay. Let's do this. So I'll also show you. This is beyond answering the question, but let's do this. This is how you can use these equations to help you. So we want to be able to say how to tell a point on the plane, right? So if I'm given a particular point, right, let's say I've got the point 1, 2, 2, is that on the plane? Well, I don't know. So, but what I can do is I can take my equation for x, y, and z. So x is equal to 1 plus t1 minus 2 t2. I'm going to rewrite it. So 2 t2 and z equals 2 t1. Okay. So now what I'm going to do is I'm going to assign that to these values here. So x is equal to 1. That comes from here. My y is equal to 2. My z is equal to 2. Okay, now I have 3 equations and 2 unknowns. T1 and T2 are my unknowns. Okay, so what I'm going to do is I'm going to plug in values for T1 and T2 and then solve for the other one. And it's going to help me. So right here, watch, I've got 2T2 equals 2. So if I solve, I'm going to get T2 equals to 1. Here, I'm lucky. I've got 2T1 equals 2. T1 equals 1. I can take these two values here and then plug them into my first equation and see if the equality works true. So I'm going to go 1 plus T1 minus 2 times T, it should be T2. I'm sorry, I did that. Oh, that was T1. I was right. Okay, and that should be equal to 1. So this is going to be 1 plus 1, 2 minus 2 is equal to 1. So 0 is not equal to 1. So no. Not on plane. The equality is false. That means that the point 1, 2, 2 is not on the plane because the equality was not true. just examples, right? We sort of went beyond what the question was asking us, but just to show you like why that would matter. Okay. If the point was on the plane, this equality would be true. 3 equals 3. That's a true equality. Then I could say that this particular point is actually on the plane. Okay. Okay. And then I'm sorry, I actually did do the example. So example 6 is that point 1, 2. It says on this triangle. We're going to actually talk about the triangle in the later chapter section. So don't worry about it just yet. Let's see. Yeah, we'll talk about the triangle in a later chapter section. I don't want to confuse you at this point here. Okay, so chapter 1.2, we come up with vector equations for a line and a plane. Okay, so what I'm going to do is, now that we finished off this chapter lecture examples, I'll scan in this lecture example packet and I'll put it up onto our web page on week 1. So wherever I post the lecture example blank page is where I'm going to post the solutions for it too. So you can take a look for that later today. Great. Okay, so with that said, very exciting. We're going to start in chapter 1.3. Anybody have any questions on what we've done so far before I move on to the next chapter section? Great. So chapter 1.3. So 1.3 is called our dot product. Now, when we talked about vectors, we talked about different mathematical properties for vectors. We talked about addition, subtraction, scalar multiplication, right? So scalar multiplication was taking a number, just a regular number, 3 or 0 or pi or whatever, and multiplying it by our vector, which meant taking that scalar number and distributing it to every component within our vector. Dot product is a form of vector-vector multiplication, okay? So this dot product is a vector multiplication. Okay, so what happens is I've got an input. I have 2 vectors as an input, okay? And then my output on the dot product is a scalar. Okay, it's interesting. I take in 2 vectors and I get a number out. I don't get a vector at all. Okay, when we talk in a later chapter section cross product, I take in 2 vectors and I get a vector as an output. Okay, but here I'm multiplying 2 vectors together and I get a scalar as an output. Okay, it's also we can generate, gives the angle between 2 vectors. So the dot product is going to tell us a lot about how these 2 vectors interact with one another. And it's also going to, we can actually use the dot product to give us the measure of the angle between these 2 vectors. Okay. What we're going to do here, we're going to focus on 2 dimensions and 3 dimensions, but you should know that the math on this will scale up to other dimensions. Okay. So let's talk about where our dot product comes from. You remember maybe in your pre-calculus class in high school, you guys covered the law of cosines. And the law of cosines is the basis for our dot product. So let's think about it. So let's say I've got my coordinate axis here. And let's say I've got, just a sec. My coordinate axis. So here, let's say I've got, you know, some displacement vectors. So I've got a vector B. And this is going to go to this point here, x2, y2. And I have a displacement vector here, A, and this is going to point x1, y1. There's a point, there's a point. Okay, and then let's say I've got a vector here. This is my vector C. Okay, so this here, we'll call this theta. Okay, so I've got these 2 vectors A and B, and theta is the angle between them. So let's say our vector C is our displacement vector from A to B. Remember, so we would go B minus A to get there. Okay, these points. Okay, so and then theta angle between my vector A and my vector B. Okay, so let's take a step back and remember what our law of cosines was. Brush off those cobwebs from high school. Cosines. So the law of cosines, but I'm going to translate it when we did the law of cosines with just triangles, we would talk about C as the length of a side. If C is a vector, I have to talk about magnitudes. So if I talk about C, I'm going to talk about the magnitude of C squared equals magnitude of A squared plus the magnitude of B squared. So far it looks kind of like our Pythagorean theorem in a sense, but then this is minus. We have to subtract out our repeats. Minus 2 magnitude of A, magnitude of B, cosine of theta. So this is our law of cosines, but we're using the magnitude of vectors to help us work through that. Okay. So if I plug in, right, if I go to calculate out A is the vector that goes from, here's our terminal, here's our initial. So I've got x1 squared plus y1 squared square rooted. That gives me my, and I square that. So I get x1 squared plus y1 squared is my A. So imagine I were to plug in all of those pieces, adds, additions and subtractions and coordinates, right? This whole thing, using our component pieces, is going to simplify. It's going to simplify to this. I'm going to first do it in R2. Okay, so this thing is going to simplify to x1, x2 plus y1, y2 equals the magnitude of A times the magnitude of B cosine of theta. In R3, it's going to look like I've got an extra z component, x1, x2 plus y1, y2 plus z1, z2 equals the magnitude of A, magnitude of B cosine of theta. Okay, so put a box around this here. Actually, wait, I'll spell it out. I'll do it in red. Okay, so let's come up with a formal definition for our dot product. Okay, so we actually have two definitions for our dot product. This part and this part. That's what our dot product is equal to, each part. This just means I take all my x components of my vectors and I multiply them together, and I add it to all the y components being multiplied together. My dot product is also equal to the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. So let's write that down. If I have v as a vector, v1, v2, all the way up to vn, right? W as my second vector, they're the same dimension. Wn, they have to be the same. If they're not the same dimension, you can't do the dot product on them. Okay, so my first definition says I'm going to go v dot w, right? So my dot product has this over-exaggerated multiply, right? It's a dot, and that's going to equal to v1 w1 plus v2 w2 plus. I'm going to keep going until I'm done with vn wn. Okay, I multiply the first components together, added to, multiply the second components together, added to, third components get multiplied together, and I keep summing that all the way up until I'm done with all of my components. The dot product is also equal to, I'm going to do this part of my magnitude of v times the magnitude of w times the cosine of theta. Okay, the cosine of theta is the angle between them. Okay, so both of these here are our definitions for the dot product. I'll let you guys write that down, and then we'll talk about like why that's important. Anybody need more time to keep writing this down? right? So what I'm going to do is we're going to talk about one of the reasons how we can figure out what the angle between them is. Let's go back to our right triangle trig and think about our axis. Here's my x, here's my y, and this is quadrant 1. And this is quadrant 2. Okay, write it. Okay, so now in quadrant 1, right? I think about I've got some kind of angle theta right in here, and I've got x and a y component that's happening. Okay, think about in quadrant 1, both x and y are both positive. Okay, so when I go to do the cosine of theta is my adjacent side all over the hypotenuse. Okay, so my adjacent is going to be positive, right? In quadrant 1, my adjacent will be positive. So it follows the x, right? This is going to be x over the hypotenuse. That's equal to the cosine of theta. Okay, so when x is positive, my cosine is going to be positive. So the cosine of theta is a positive number in quadrant 1. And it's positive because it's based on my x, right? And x is going to be positive in quadrant 1. Okay. Let's think about it in quadrant 2. Here, what I have is a minus x and a y. My xy points, my x is negative and my y is positive. Okay. So because my cosine is based on the x, right? My cosine of theta is going to be negative in quadrant 2. Okay. So now let's think about like what that means. What does that tell us? So we're thinking about where cosine is positive and negative, and what do these angles look like? So let's remember also back to geometry too. So if I've got, let's say for example, here's my vector A, here's my vector B, and then here's my theta, my angle between them. Okay. So now when A and B, when the angle between them is less than 90 degrees, right? So theta is called an acute angle. It's less than 90 degrees, okay? Or it's less than, if you work in radians, pi over 2 radians. Okay, that's my acute angle. Now let's say I've got my vector A and I have my vector B, and the angle between them is equal exactly to 90 degrees, okay? This is a right angle, which is equal to 90 degrees, or it's equal to pi over 2 radians. Okay, so it's a right angle. Okay, I'm drawing this out because it's important. Our dot product is going to tell us stuff. Say here's B, here's A, here's our theta. Okay, when our angle is greater than 90 degrees, it's an obtuse angle. Okay, which means it's greater than 90 degrees. Okay, it's less than 180, but greater than 90 degrees, which means it's greater than pi over 2 radians. Okay, so it makes it an obtuse angle. So 91 degrees is an obtuse angle, even though it'll look like it's, you know, right angle, but it's 91. It's an obtuse angle. So now our dot product is based on the cosine of theta. So let's think about what's happening, okay? If the cosine, angles that are less than 90 degrees put us solidly in quadrant 1. That means that our dot product is going to be a positive number. So I would say A dot B is equal to some positive number. So when I go to do the dot product and I want to know, is this angle between them acute, right, or obtuse, okay, I can take the dot product and see, is it positive, negative? If it's positive, then I know I'm dealing with an acute angle, okay? Let's do this one here. We'll come back to the right angle in a minute. So now an obtuse angle puts us, right, puts us into quadrant 2. Remember we said before that quadrant 2 means that our cosine is negative. So that means that our dot product is negative. Negative. So we'd say A dot B is equal to a negative number, okay? So that's going to tell me that the angle between these two vectors is going to be obtuse because my dot product will be a negative number. We're going to go through examples so you can see how this works. Now, let's talk about our right angles, okay? When I go to do the cosine of 90 degrees, so the cosine of pi over 2, cosine of 90 degrees is equal to 0. Now, why is that? Because when I'm looking here, right, my x, right, my 90 degrees, this is my right angle here, my x is equal to 0, right? I'm sitting right on top of the y-axis, my x is equal to 0. So my cosine of 90 degrees is equal to 0. That means that my dot product is equal to 0. So I would say A dot B equals 0. So because of that, the dot product becomes actually an important test to tell if two vectors are perpendicular to each other. So I'm going to write that. So when the dot product is equal to 0, two vectors are perpendicular to each other, right? So I can write that out in math. So I can say if A dot B equals 0, then A is perpendicular to B. It's important. We're going to find out later on in other chapters. We're building up a toolkit right now. We're going to find out later on in other chapters that knowing that two vectors are perpendicular to each other means that I can do other things with them. Okay, so a dot product becomes our test to see if two vectors are perpendicular. Okay, so let's keep that in mind. All right. Before I do any examples, I just want to give you guys some extra properties about the dot products and mathematical things that we can do about it. And then we'll go into some examples and then we can practice some of this stuff. Does anybody need more time to finish writing? You guys good? If you don't tell me, I'm going to assume you're okay. All right, so let's do this. So some theorems, some properties. Dot product. Okay, so we're going to assume A, B, and C are vectors in whatever dimension. The dot product is going to scale up to dimensions higher than 2 and 3. Okay, but we're just going to specify that as R with N as a superscript. R and S are real numbers. Okay. Real numbers. Okay. All right, so our first property is this. A dot B is equal to B dot A. That's important. We find when we do the cross product, that's not the same. Okay, there's an order to a cross product, but for the dot product, it's not. We're adding. We're going to multiply, right? First components times first components with second components plus second components. We're adding things up, so it doesn't matter what order we do it in. Okay, I can go A dot B plus C. Both B and C are vectors, remember? And that's, I can distribute this out, which is the same thing as saying A dot B plus A dot C. Conversely, I can factor out the A and just add these two vectors and do one dot product. In terms of computational cycles, right? Addition's cheap, multiplication is a little more expensive. So maybe I want to have only one multiplication instead of two. So if I see this, I can factor out my A vector. 3, if I have a constant R times A, and that's dot product with a constant S times B, that's the same thing as saying, I'm going to multiply the two constants together, and I'm going to multiply that by their single dot product. Okay, so in terms of computations, this can be cheaper than that one, right? Because I'm not multiplying out all those individual components. Right? I'm just going to multiply these two scalars and then multiply it by that one scalar at the end. Okay. last one, if I take the dot product with itself, that's another way of saying, let's do the magnitude squared. Okay, so that's what that looks like. Okay. Now, if I want to find out the actual measure of an angle, okay, remember how we said I can go the magnitude of A times the magnitude, oops, sorry, that should be a B, cosine of theta is equal to A dot B. Okay, but now if I want to find out, this is my property 5, if I want to find out what's that angle measure, okay, this, I can divide both sides by the magnitudes. So I'm going to get, it's going to look like cosine of theta equals A dot B divided by magnitude of A times the magnitude of B. Remember, A dot B gives us a scalar. Magnitude of A is a scalar. Magnitude of B is a scalar. You multiply, this is going to give me a number. So to solve for theta, I have to take the inverse cosine. Theta equals inverse cosine of A dot B all over magnitude of B. That becomes important. We're going to be wanting to do that. Your inverse cosine is, see these buttons here, that sine -1, cosine -1, tangent -1. They're right above those sine, cosine, and tangent buttons on your calculator. Okay. So to find the angle measure between the actual angle measure, you would take the inverse cosine to do that. Okay. All right. So we'll work through an example just so you can see what that looks like. We'll go through and we'll do these things here. Okay. Calculate out our angle measures. Okay. You guys all have this here before I pull out the example page? Pretty good. Nobody says anything. I'm going to assume you have it. Okay. So we've got these following vectors here, A, B, and C. Okay. We want to be able to find out, we're going to do vector pairs, A to B, A to C, and B to C. So we're going to take the subsequent dot products, and we're going to find out, you know, are the angles between them acute, perpendicular, or obtuse, and then what are the angle measures. Okay. Let's do part A first. So I'm going to do A dot B. So I'm going to take the dot product of these two vectors here. So I'm going to go like this, 1, 2, 3, dot, -2, -2, 2. Remember our dot product, we take our x components, so 1 times the -2 plus my y components, 2 times the -2 plus my z components, 3 times 2. See how I did that? I multiplied first components by first components, second by second, and third by third. This is -2 -4 plus 6. That's -6 plus 6. This is equal to 0. Remember we said before, right? If the dot product was equal to 0, that means that these two vectors are perpendicular to each other. A and B are perpendicular because the dot product was equal to 0. We'll prove it to ourselves in a minute when we actually take the, we find the actual angle measures in part B. Okay, so A dot B, we'll do A dot product with C. So 1, 2, 3, dot with C, so 0, 4, 1. Okay, so watch what I'm going to do. First component to first component. So 1 times 0 plus second component to second component plus third component to third component. So 1 times 0 is 0 plus 2 times 4 is 8. 3 times 1 is 3. This is equal to 11. It's a positive number. Right? We said that when the dot product was positive, we're talking about an acute angle, okay, between A and C. Let's do it again for B and C. Okay, so B is -2, -2, 2, dot product with 0, 4, 1. Okay, so first component, -2 times 0 plus second components, -2 times 4 plus third components times 1. This is 0 plus -8 plus 2. That's equal to -6. It's a negative number, which means we must be dealing with an obtuse angle. We're going to prove it to ourselves in a minute because we're going to take the, we're going to calculate the actual angle measures. Okay. Everybody see how I did the dot products here? You good with that? Okay. So let's do the angle measures. Okay, so to do the angle measures, I actually need the magnitudes of A, B, and C. So the first thing I'm going to prefetch that. I'll calculate the angle measures, the magnitudes. So the magnitude of A, it's the sum of the squares of each of the components. 1 squared plus 2 squared plus 3 squared, and I have to take the square root of it. So 1 plus 4 plus 9, that's going to give me 14 inside the radical. I'm just going to leave it as radical. I won't worry about simplifying it. And definitely don't give it to me as a decimal. Just leave it in terms of radicals. So for B, okay, so B, watch out. I've got a -2 squared plus a -2 squared plus a 2 squared. Oops, sorry, can't see that. Okay, so make sure you're using parentheses on here so that you actually get a positive number. So this is going to be 4 plus 4 plus 4. This is radical 12. You should never get a negative inside your radical. If you do, probably you forgot to put parentheses. We'll calculate the magnitude of C. It's going to be 0 squared, well, 4 squared plus 1 squared. 0 plus 16 plus 1, that's radical 17. So I've got now the magnitudes for each here. Okay, so now what I want to do is I want to calculate the angles between the various ones. So I'm going to do theta as our angle between the vector A and the vector B. Okay, so that's our first one. So I'm going to go theta equals my inverse cosine. Remember what we said? This was going to be the dot product, A dot B, which we said was 0, divided by the magnitude of A times the magnitude of B. Now I'm showing you, inverse cosine of 0. We know what this is going to be. This whole thing is going to be a 0 in here, but I'm just putting in the values so you can see what I'm going to get. When I do this, I'm going to get 90 degrees. Give me your answers in degrees or radians. Either way is fine. Just tell me what it is that you're doing. So this is pi over 2 radians. Okay, either one, I'll accept both as an answer, but I need the units, okay? So angle between, the other one, A and C. So I'm going to go again, theta equals my inverse cosine. So my values, my dot product between A and C, 11 divided by 14 times radical 17. So inverse cosine of the dot product divided by the magnitudes. Don't forget inverse cosine. So when I do this, I get 44.5 degrees, or I can do 0.77 radians. Either one is fine. Okay. And the last one, my theta between B and C. My theta inverse cosine. So our dot product was equal to -6 all over radical 12 times radical 17. Right, so the magnitude of B and the right magnitude of C, we're going to divide that into the dot product, take the inverse cosine of that, and I got 114.83 degrees, or 2 radians. I don't care which you want to give me, just make sure you give me the units so I know that you know it's degrees or radians. Okay. What do you guys think? Any questions? So confusing. Somebody have a question?
I said it's a little confusing.
It's a little confusing?
Yeah.
Yeah. It's a practice. We're going to end up practicing a lot, but you can think about it like this, that I've got 2 vectors, okay, and the dot product is a mathematical process of multiplying 2 vectors together, okay? So when I take the dot product between them, okay, it's going to give me a scalar, okay? Now, it's also going to give me, I can use it to calculate the angle measure between these 2, okay? Let's see. All right, you guys okay with this example? let's do another example. I want to show you with the standard basis vectors. Remember we talked about the I, J, and K. This is example 2. Our standard basis vectors calculate the following dot product. Okay, so now there are multiple ways of doing this. I'll show you two ways. One of the ways I like the best is the simplest one. But let's remember our basis vectors. So this is I, J, and K. So that means I have 3 dimensions because I have a K in there. So J is equal to 0. My Y component, my K equals 0, 0, 1. Okay. So now what I can do is I want to actually mention out. So I dot I is equal to 0. I'm sorry. I dot I is equal to -1, positive 1. J dot J equals positive 1. K dot K equals positive 1. I dot K equals 0, and J dot K equals 0, and J dot I equals 0. And why that is, we can do this out in terms of multiplying our first components together, multiplying our second components together, third components, and adding them all up. You can see that you're going to get zeros. Whereas if I were to multiply I times I dot product, I'm going to get a 1, right? Because it's 1 plus 0 plus 0. So now let's do this. If I'm going to multiply these together here, okay, there's a couple different ways to do it. So the first vector is equal to, I'm going to write it out, 3i minus j plus 2 times k. It's just the coefficients here. So that's 3 minus 1, 2. Okay, that's my first vector. My second vector, now I don't have a k. That's almost like saying my coefficient for k is equal to 0. So if I go I plus j plus 0 times k, because it's going to be the same dimension, then I'm going to go 1, 1, 0 is my second vector. So when I go to do this dot this, these two vectors dot product together, that's the same thing as saying just their coefficients. Okay, so all I did was strip out the coefficients for I, J, and K, and I turned them into vectors, just 3-dimensional vectors. So now if I go to take the dot product, that's going to look like first component to first component plus second component to second component plus third component to third component. I'm going to sum all them up. So 3 times 1 minus 1 times 1, 2 times 0. So 3 minus 1 is equal to 2. That's the simplest, most straightforward method, okay? The other method that I can do when I have the basis vectors is kind of treating it like an equation where I have to distribute all the terms and multiply it out. I'll just show you really quick, but I think your best bet when you see basis vectors being dot products together is to write them in terms of their individual components and then just take the regular dot product. So let's do this. I can also do it like this. So 3, let me write it down, J. I'm just rewriting the question. And I'll write out I plus J. Okay, so I can do this out like, I'm gonna sort of, it's like FOIL, but I'm distributing it to all these terms. So I go first, so 3i dot I plus 3i dot J. So I did this one times this one plus this one times that one. I'm gonna do this one here, minus J dot I minus J dot J. So I'm multiplying this one and this one plus 2 times K dot I plus 2K dot J. It's much more cumbersome. I really prefer using just the coefficients because it's just numbers in that way. So the only ones I need to worry about are the ones that have the same piece, because remember, like we said before, if it's I dot J that goes to 0, J dot I goes to 0, K dot I goes to 0, and K dot J goes to 0. So the only ones I have to worry about are these two right here. So this becomes 3 times I dot I, and this becomes plus minus J dot J. Okay, so I dot I was equal to 1, and this is almost like saying minus 1 times J dot J, right? And this is equal to 1 here. So 3 minus 1, which is equal to 2. I get the same number in the end. It's just a lot more algebra that I have to worry about. Okay, if you're looking at basis vectors, my suggestion for you is strip them in terms of their coefficients. I, J, and K become 3 minus 1, 2 as a vector. ij 0k 1 1 0. Okay, and then I can just take the raw dot product. And then this is just to show you that you can do it this way. Okay, it's a lot more algebra, and it's, you know, you have more places to make mistake. It's a little less straightforward. Does anybody have a question about how we did the dot product method here?
Yes, can you re-explain it?
Yeah, sure. So with the dot product, it's always, I take my first component and I multiply it by my first component over there. So I've got two vectors. I always take in two vectors, right? And I strip them into individual components. So I do first component times first component. So 3 times 1 plus. And I take the second component and I multiply it by the second component here. -1 times +1. Plus, I do my third component by my third component, 2 times 0, and I add that together. So I'm taking my dot product. The whole definition for the dot product is I take out each component, the x components, the y components, and the z components, right? And I multiply those x components together, and I add it to, when I multiply the y components together, and I add it to the z components together. And then I just sum it all up, and I get a number. That's why I showed it at the beginning that it comes from our law of cosines, so you don't think I'm just coming up with this thing, you know, out of thin air, okay? But the dot product is a process of multiplying two vectors together.
I'm sorry, I meant that last part, the part under that. I'm sorry.
The math, the algebra part?
Yeah.
Yeah, I'm showing this to you as an example that there's another method of doing it when you do the basis vectors. It's got more algebra to it, but it's like, I've got, we were given it initially like this, right? Where I've got the 3i minus j plus 2k. This is the same way of representing a vector like this, right? Because it's like a linear combination with the basis vectors. Remember, our basis vectors were, I was at 1, 0, 0. It just represented things in the x direction. J represented things in the y direction, and k represented things in the z direction. Okay? And so that's all that meant. So it was like, here's our x, here's our y, here's our z. This is I, that's a 1 unit. This is j, that's a 1 unit. And that's k, that's a 1 unit. Okay, so these are our basis vectors. So now when I do it this method here, right, I'm gonna do like imagine if this was an equation, 3x minus y plus 2z, right? And I wanted to multiply it all out. I said, go ahead and distribute this out, give me one, combine all the like terms, and give me one equation, right? You would take this first term and multiply it by these, by this one, and then add it, take that first term. So you're gonna distribute it like you would in like algebra, right? So I did the same thing, but now I have a dot product. So when I say this term, dot product this term, plus this term, dot product this term. Then I move down to here. This term, dot product this one, plus this term, dot product that one. And I move down. This term, dot product this term, get here. This term, dot product that term, and I get there. Okay. Now, I just gave it to you.
Distributed.
Yeah, all you're doing is distributing it.
Yeah.
And the trick to remember is you're only worrying about when I have the same basis vector, so I dot I and j dot j. If we had a k dot k, then I would include that as well, but we don't. So I dot I, j dot j, those are the only ones. All the other ones reduce down to 0. Because when I take the dot product of I and j, right, if I multiply first components together, second components together, and third components together, and I sum them all up, all I get is a big 0, right? So that's why all of these other terms reduce down to 0, and I'm only worried about this one and this one. I dot I is equal to 1, j dot j is equal to 1. So I have 3 minus 1 gives me 2. It should be the same answer as before. It's just more math, more algebra. Does that make more sense?
Yeah, thank you.
You're welcome. All right. So there's another portion, an idea of how we take the dot product and we apply it into something called a projection. We only have about 5 minutes left, or a few minutes left of the class, so I'm going to wait until Wednesday's class to talk about the projection and how we do it. But what I'd like to do is if you guys want, if you want to take a look at some of the classwork problems, we have dot products that we can work on, right? And we also have a classwork for 1.2. I'll start working through on the screen here for the next few minutes. This is the classwork for 1.2, okay? Before we get to the quiz for 1.1 and 1.2, I'll post solutions for the classwork problems so that you guys can see those. But in the meantime, I'll just start working through some of this classwork here, okay? And then tomorrow's class, we'll pick up and then we'll do the last topic, which is an application for our dot product, okay? So I'll start working through this classwork here. You're welcome to work on it now as well. Remember, you're going to have to pass it in at some point. So if you want to watch me as I work through it, then you can. That may help. All right. So I'm just going to.
When we submit them, we just take pictures of them and upload it to Canvas, right?
Exactly, right. And then when you go to submit it, then it'll only take a PDF or a JPEG. PDF is my preferred because I can grade it much more easily. I can make comments on it. JPEG is much harder to edit. But I think most phones, you can download a free app that'll convert a picture into a PDF. I recommend doing that. Or if you have a scanner, you can save it as a PDF. But yeah, you'll upload that PDF into our Canvas page. And
oh, I'm sorry. It's the classwork, the homework, and the quiz that's due on the 17th, right?
Yeah, I know it's a lot, right?
Yeah.
But remember, it's not all hope isn't lost. So the classwork, I just need to see that you've tried it, that you've made a concerted effort. You don't even have to do the whole thing, but that you've at least tried these problems. And normally in class, like we would just be working on this stuff in class, and people would come up and ask me questions about it, and they would check their solutions, which is why I'm gonna work it through now. But I just need to see that you were trying it, okay?
Yeah.
And then the homework, you actually have the homework solutions posted on our Canvas page. It's part of that reading material at the very beginning of our Canvas page. So in theory, if you're falling behind, you can just copy down the answers to the homework. But I need the homework solutions. And then those will be due on Thursday as well. But the quiz itself is I'll have a 24-hour window of availability. So the quiz won't happen during our class time. But I'll start the quiz at like noon on Thursday, and it'll go till noon on Friday.
Okay. And where did you say that reading part is on Canvas? I just don't see it. I just see
it's under modules. So if you go to the modules page, right, on the modules page at the very top. So the rest of the modules page is organized by week 1, week 2, week whatever.
Yeah.
But at the very top of that it should say reading material. I think that's what I called it. And then on that reading material, right, there should be a whole bunch of stuff. And sometimes there's like an arrow, like a little triangle that if you click on that, it'll expand it.
Okay.
Then you can see all that stuff. Is it showing up for you?
Yeah.
Okay. Right. Okay, so I'm going to start for the next few minutes. I'm going to do some of this stuff. I think we're probably close to being out of time, so you're welcome to leave. But I'll just work through this first problem here, and then we can we'll meet again on Wednesday.
I have a question about the homework.
Oh, yeah. Listen, is it really quick? Because we can talk about it in office hours as well. What question did you want to ask?
Well, because I just downloaded the homework file and there are like 30 questions on them. But I know that for this week, we only need to submit homework for chapter 1.1 and 1.2.